Dropping a massive star into its own gravitational field transforms the topology of spacetime itself, creating an inescapable region bounded by a smooth, three-dimensional manifold. We model universe geometry as a four-dimensional differentiable manifold equipped with a Lorentzian metric tensor that dictates the light cone structure at every point. The Lorentzian metric splits the tangent space at each point into time-like, space-like, and null vectors, determining which regions can communicate causally. To define a black hole rigorously, topologists examine future null infinity, the asymptotic destination of all outgoing light rays escaping to infinity. The event horizon is precisely the boundary of the causal past of future null infinity, separating paths that escape from paths trapped forever.
This definition requires the manifold to be asymptotically flat, meaning its geometry approaches standard Minkowski space at immense distances from the mass. This horizon acts as a topological one-way membrane because light cones tilt inward, forcing all future directed world lines to cross only in one direction. Hawking proved that for stationary four-dimensional black holes satisfying the dominant energy condition, the spatial cross-section of the horizon must be topologically spherical. This means the two-dimensional surface cannot possess handles like a torus. Its Euler characteristic must equal 2, enforcing a strict sphere geometry. The dominant energy condition ensures that matter local energy density is non-negative, and energy flow is time-like or null, preventing unphysical topological disruptions. Unlike the globally defined event horizon, an apparent horizon is a local boundary, defined as the outermost marginally trapped surface where outgoing light expansion vanishes. Inside the apparent horizon, the expansion of both outgoing and ingoing orthogonal null geodesics is negative, meaning the area of the light wavefront decreases. Roger Penrose proved that if a trapped surface forms and the energy condition holds, spacetime must contain at least one incomplete, inextendable geodesic. Geodesic incompleteness means that particle histories terminate abruptly at a finite proper time parameter, indicating a breakdown in the smooth manifold structure. Technically, the singularity itself is not a point inside the manifold, but a singular boundary where curvature invariants diverge toward infinity.
As paths approach the singularity, the Kretschmann scalar invariant blows up, causing infinite tidal forces that destroy any physical structure. The simplest solution is the Schwarzschild metric, describing a static, spherically symmetric black hole with a spatial topology of three-dimensional Euclidean space minus a point. Historically, the radius equal to 2 times the mass times the gravitational constant divided by the speed of light squared appeared singular, but this was a coordinate artifact. Transforming to Kruskal-Sekaris coordinates removes the coordinate defect at the horizon, revealing that the metric remains completely smooth and differentiable there.
The maximally extended Schwarzschild geometry contains 2 distinct exterior asymptotically flat regions connected by a wormhole. This dynamical spatial channel is known as an Einstein-Rosen bridge, representing an untraversable tunnel connecting 2 separate universes or distant parts of the same universe. This Einstein-Rosen bridge pinches off so rapidly due to gravitational forces that no light ray can pass through from one exterior region to the other. Any observer attempting to cross is crushed in the singular region before reaching the opposite side, rendering the topology dynamically non-traversable.
The topological censorship theorem proves that in general relativity, any non-trivial topological structure, like a wormhole, cannot remain open long enough for light to cross. Averaged energy conditions guarantee that gravitational attraction causes the throat to collapse faster than information can propagate through it. Rotating masses are governed by the Kerr metric, which exhibits a more intricate topological structure than the static Schwarzschild solution. It features 2 distinct event horizons, an outer and an inner horizon, which surround a ring-shaped singularity rather than a point-like center. Outside the outer event horizon lies the ergosphere, a region bounded externally by the static limit surface.
In this zone, the killing vector field responsible for time translations becomes space-like, meaning that staying stationary relative to infinity is physically impossible. Within the ergosphere, the frame-dragging effect of the rotating black hole is so absolute that space-time itself is dragged at the speed of light. All physical objects and light rays are forced to rotate in the direction of the spin, allowing energy extraction via the Penrose process. Passing through the outer event horizon leads toward the inner horizon, which functions as a Cauchy horizon. This boundary marks the absolute limit of predictability for the Einstein field equations, beyond which deterministic initial data no longer uniquely determines the future evolution of the spacetime manifold. Passing further inward leads directly to the ring singularity, located in the equatorial plane. Because this singular boundary has the topology of a ring rather than a point, incoming geodesics that do not hit the ring precisely can pass straight through its central opening. Traversing the center of the Kerr ring singularity transitions the observer into an exotic spacetime extension characterized by a negative radial coordinate. In this region, gravity becomes effectively repulsive, and the local topology permits paths that loop back on themselves in time. These paths are known as closed time-like curves, which represent physical trajectories where an object's tangent vector is always time-like, yet the world line forms a closed loop. Topologically, this introduces causal loops into the manifold, allowing an observer to potentially interact with their own past. To protect causal predictability, the weak cosmic censorship hypothesis conjectures that all realistic singularities arising from gravitational collapse must be hidden safely behind an event horizon. This ensures that the singular boundary cannot influence observers located out at future null infinity. If a singularity forms without a protective event horizon, it is classified as naked. A naked singularity destroys global predictability because arbitrary, uncalculable physical information could emerge from the singular boundary, preventing us from predicting the future state of the universe from initial data. The strong cosmic censorship hypothesis states that physical spacetimes must be globally hyperbolic, meaning that the Cauchy horizon inside a rotating black hole is highly unstable. Any realistic perturbation causes this boundary to transform into a physical singularity, preventing observers from entering non-deterministic regions. This instability is driven by mass inflation, where infalling radiation from the outer universe becomes infinitely blue-shifted as it piles up at the Cauchy horizon. The local energy density and curvature blow up, turning the smooth boundary into a lethal singular shockwave that terminates spacetime. Extending general relativity to 5 or more dimensions breaks the strict topological uniqueness theorems found in 4 dimensions. In higher dimensional manifolds, gravity allows for a rich variety of stable black hole solutions, possessing horizons with non-spherical qualitative spatial structures. In 5-dimensional spacetime, a black ring solution can exist, where the event horizon exhibits the product topology of a circle multiplied by a 2-dimensional sphere. The ring rotation provides a centrifugal force that counteracts the gravitational attraction, keeping the toroidal structure stable. When higher dimensional black holes collide or evolve, the event horizon topology can dynamically transition, changing from a sphere to a ring. This bifurcation passes through unstable, highly singular intermediary configurations that challenge our mathematical understanding of smooth manifold evolution. At the subatomic Planck scale, quantum gravity theory suggests that the smooth manifold description of spacetime breaks down entirely. Spacetime becomes a violent quantum foam, where microscopic black holes and virtual wormholes continuously form and annihilate, causing rapid fluctuations in local topology. Hawking radiation causes black holes to evaporate over time, leading to the profound information paradox. If a black hole completely vanishes, the trapped quantum information appears lost, implying a non-unitary transition where a pure quantum state evolves into a mixed state. The holographic principle resolves this dilemma
by asserting that the quantum states within the bulk of a spacetime manifold can be completely encoded on its lower dimensional boundary. Therefore, information never truly enters the black hole interior, but remains accessible on the horizon surface.
String theory resolves the singular boundary by replacing point-like zero-dimensional particles with extended one-dimensional strings. Because strings have a minimum length scale, they cannot be compressed into an infinitely small point, effectively smoothing out infinite curvature densities into smooth geometric structures. A spacetime manifold is defined as globally hyperbolic if it contains a Cauchy surface, which is a spatial slice intersected precisely once by every inextensible time-like curve. This topological condition guarantees that physics remains completely deterministic throughout the entire evolution of the universe. Mapping the qualitative global structure of event horizons, apparent boundaries, and singularities provides the necessary mathematical framework for a complete theory of gravity. These topological methods allow physicists to rigorously analyze the limits of predictability, causality, and the geometric structure of space and time.